recording. Okay, so what is an exponential function? All it is you have your input as an exponent. So x is the exponent. So b is the base. That's the constant. Now b is going to be greater than 0 because it's weird if it's negative. Because if you have, like, say, negative 2 to the x power, let's say, then I'm not sure what to think of that, right? That's really weird because it could be positive or negative. It would oscillate in some ways. Like, for example, if x is odd, y is negative, x is even, it's positive. Also, what if you have a fraction, right? What if you have like negative 2 raised to the 1/2 power? Then it's going to be imaginary, right? So it just gets really weird when the base is negative. So we never have negative bases for exponential functions. They're always going to be positive. They're not going to be 1. I mean, it's not a big deal if it's 1, but what happens if you have y equals 1 to the x power? What is that just really telling you? It's just what? 1. And that what kind of graph is that? Just a flat line, right? So how is that even exponential? That's because exponential usually has to show some sort of sharp increase or sharp decrease. That's what something's decaying exponentially or growing exponentially. There's a heavy change that's happening with y as x changes. And of course, there are different scenarios you have to consider when b is between 0 and 1 or when b is bigger than 1. And we're going to explore that in just a little bit. But again, we don't really have b equals 0. That's kind of weird. B equals 1. That's kind of weird. B is less than 0. That's weird. If b is 0, that's just 0, right? So again, b is positive. B does not equal 1. And the domain's all real numbers. There's no reason why you restrict x. If it's an exponent, what do you do? Like, put whatever you want. It's not a big deal. But the base has some restrictions. It's between 0 and 1. That would be decay, which we'll talk about in a few minutes. Bigger than 1, we'll call it growth. Now, let's actually talk about evaluating. Pretty simple stuff. This is just calculator work. I think you know what to do here. Just do that. Or here. That's also kind of weird. If you have a negative exponent, what does that do to the base? Do you guys remember? What happens to the base when the exponent's negative? It flips, yeah. So you could rewrite it like this and change the exponent back to positive. You totally can do that. That totally can happen. So in essence, even though your base is bigger than 0, because the negative exponent causes the base to flip or reciprocate, and then it becomes a decay function. But if I were to plug this into a calculator, which actually, let me get my TI-84 calculator right now. I have an app for it. Nope, should be math department. I know this. Okay. Here we go. Perfect. 0.6 raised to the 1.5 power. Yeah, I mean, whatever, right? I mean, that's just pretty easy stuff. 0.465. And next one, 3 times 0.5 raised to the pi power. 0.340, we'll say. Okay, so all makes sense? We're good? Okay, cool. Let's keep on moving. Graphing should be very straightforward. Just a bunch of numbers are going to plug in for x. First of all, the domain's all real. We know this. We'll worry about range in a little bit. We'll worry about horizontal asymptote in a little bit. Let's fill out this table. What's 2 to the 0 power? What's 2 to the 1 power? 4, 8. And that's 1/2, 1/4, and 1/8. So if you plot the points, oh, hey, Liam, I'll get your notes for you. You have 1/2, 1/4. It's awfully hard to draw like 1/8. But what do you think is going to happen as x gets more negative? As x approaches negative infinity, what do you think y is approaching? Exactly, right. Now, does y become 0 exactly? No, and why? It never will. The reason why is that what's your base here? It's 2, right? So you're multiplying 2 over and over again. That's all this really means, right? That's basically 2 multiplied a bunch of times. What if you have x to, say, negative 10 power, let's say. Say x is negative 10. So it's 1 over all this junk, right? Here's the thing. Overall, your fraction is 1 as a numerator, and the denominator is just a bunch of 2's. For this fraction to equal 0, what has to be true for this fraction to equal 0? What has to be true of the numerator? If you want the whole thing to be 0, the numerator has to be 0. But it never will be, because of the nature of this function, right? There's no way we're going to hit 0. In fact, there's no way y is ever going to be negative. How can y be negative? How can I multiply 2, a positive number, a bunch of times and make it negative? It just can't happen. So it can't go below the x-axis either. So in this case, we have something called an asymptote, which is like this. Now, I'm going to warn you. Some people think, so this is a total misconception. And we're going to clear this misconception today. And don't do this misconception down the road, especially if I teach you calculus next year. I'll be very upset. Don't do this. It is not a boundary that cannot be crossed. And that's a double negative. You can cross horizontal asymptotes. Sometimes we cross them, and sometimes we don't. Oh. All depends on the equation. Okay, so that's what, first of all, let's clear that misconception, okay? So you can cross them, or maybe you don't. It just depends, and every situation is unique. Sometimes you do, sometimes you don't. What it really is, and let's switch colors here. What it really is, it describes how the ends of the graph will look, or basically what y does when x goes towards positive or negative infinity. That's all it ever is. Don't do the red, do the green. Okay? Actually, I didn't mean to color like that way, but I guess it's good. Stop this kind of thinking, do this kind of thing, right? Stop, go. Do not think it's a boundary. You can cross horizontal asymptotes. Actually, we did rational functions. We crossed them. You can. For exponential functions, because the way they're, because of their nature, we don't cross them. It's just it does look like a boundary or a floor or a ceiling, whatever you want to call it, or a basement. They go towards. But really, it's all about just how does the graph look. If you were to actually extend this graph more to the left, it looks like a horizontal line. In fact, it looks like y equals 0. That left end, that left arrow looks like y equals 0. It's not y equals 0. It's y equals 0.000001, but it's pretty darn close to y equals 0. So we're going to say that the horizontal asymptote is y equals 0. And the range, we're going to say this. So there is kind of a limit. You want to think like that. And that's actually kind of the beginnings of calculus. Calculus talks about limits, limiting behavior. There's a limit that y approaches. If y approaches 0, as x goes towards negative infinity. Now, as x goes towards positive infinity, what's y doing in this case? Yeah, and that's going up like crazy. So when you hear something increasing exponentially, that means it's increasing quickly, or decreasing exponentially, it's decreasing quickly. A lot of times, like when people get sick, like, you know, the infection rates increase exponentially because if all of a sudden 4 people are sick, then 16 people get sick, then like 64 people get sick, and so forth. It's COVID is kind of the same thing. And then, of course, there's a limiting factor, which I don't want to get into. That's another type of function. But for now, we're just focused on exponential. So that's what's happening there. All right. Oh, question, Liam? You get more from the notes? Sorry. You good? Okay, cool. All right. Now we're going to talk about transformations of these. You can move these around. They can shift left and right. They can go up and down. They can stretch. They can reflect. So if we look at D first, D is kind of the easiest to deal with, and it's the most intuitive. If D is positive, go up. If it's negative, go down. That's simple. And Desmos is actually your best friend here. Desmos is your best friend when you're trying to understand graphs. Y equals 2, and you hit shift 6, that makes an exponent. And if I put a +1, up 1, up 2, up 3, up 4, -1, -2, -3, -4, and so forth. Easy peasy, right? Not that hard. C is always counterintuitive, the horizontal shifts. Like people think, oh, X -1, it goes 1 left. No, it actually goes 1 right. So if I do, so I have to go up to where X is. See, it's hard to tell. But this dot here, 0, 1, became 1, 1. I know it looks like it shifted down, but it actually shifted 1 to the right. Oh, no, I meant to do this. Wait, what the heck's wrong with me here? X. Okay, it's being really dumb. Okay, never mind. Okay, it did shift 1 right. Sorry, that was weird. I don't know why I did that. Yeah, anyway. So it shifted 1 right. Was that we have a point at 0, 1, now we have a point at 1, 1, right? So that's what's happening there. Anyway. And of course, if I do +1, it went left 1. Then H does a stretch, and that's kind of hard to tell too sometimes. If I do 3 times that, it's a little steeper, I suppose. Or if I do 0.5, it's a little more flatter, I guess. I mean, it becomes more pronounced if I do like 0.01. See how it's really flat? If I put a negative in front, it flips. So it's all the same stuff as before. And the range will be altered as a result if you do flip. If you have ace positive, ace negative. And the vertical shift tells us the range, right? Because that also tells us the horizontal asymptote. You can memorize all this stuff, but I think it's better just to visualize it, and you don't have to really memorize it. But yes, everything you need to know about transformation is all right here. So to do this graph, just should be pretty straightforward. Here's g of x. We know we're going 1 left. The asymptote won't change. It'll still be y equals 0. The range will still be this. The domain is still all real numbers. That never changes. And if I make a quick table, so for this guy, usually I'll do a table for the parent function. I'll do 0, 1, and -1 as my typical points. So here, if I add, so I got to take 1 away. Hold on a sec. Why am I confused? Never mind. Sorry, I just confused myself. So here we go. -1, 1, 0, 3. Right? Does that make sense, right? We're okay with that. Whereas the parent function, if I were to graph the parent function, it would look like this, right? See how it's shifted, right, from the green? That makes sense. You don't have to graph the parent function, just graphing g of x. And that just went 1 left. Questions? No? All right. Pretty easy, right? Okay, this is a decay function because your base is between 0 and 1. So this is decay. We're going 3 down. So your range is from -3 to infinity. Still all real numbers. The asymptote y equals -3. Zero, 1, and -1. If I plug those in, I should get, well, let's look at the parent function first. So what I'd like to do first as my strategy of transformations is consider the parent function, make a quick table for the parent function, and then adjust, transform, change, put a new function. That's what we call a transformation. Transformation means a change in general, right? That's what we want to do. We want to change it. So 0, 1, 1 half, -1, 2. And we're subtracting 3. So 0, -2, 1, -2.5. And there's a horizontal asymptote right here. So once you get the hang of this, you kind of want to identify the horizontal asymptote kind of right from the get-go, because then you kind of just know what it's heading towards as you draw it. As x gets bigger, in this instance, y is approaching -3. Okay. Questions? Not pretty easy stuff. Okay, cool. All right. Why don't you guys try this one here? I'll give you guys I'll tee it up a little bit using a good golf analogy with Masters. So I'll tee it up here. 0, 1, and -1. So that's 1, 3, and 1/3. So we'll make a table up. Let's go off to the side. So you'll need to do a is -1, remember. H is 3, and k is 2. Because h is 3, you're going to add 3 to x. Here you're going to multiply y by -1. Here you're going to add 2 to y. But remember, if you're doing two things to y, which one comes first, multiplication or addition? PEMDAS. Which one comes first? PEMDAS. Multiply, good. You're going to multiply first, then add afterwards. So what you'll need to do is update this by 3. And here, you'll need to multiply by -1. Then, I put in caps so you don't mess it up. Then add 2. Okay. I'll be right back. Back about 15 seconds. Okay. More solid graphing looks like. Okay. All right. Well, it should be pretty straightforward. All right, so cool. Your table should look like this, guys. Should have 3, 4, and 2, right? And then y, multiply by -1, then add 2. So you should have 1. Multiply by -1 and add 2. You should have -1.
Wait, why is it 3, 4, 2?
At 3 for x, right? No, I can please question me if I make mistakes. -1/3, add 2 should be 5/3, I think. So 3, 1. 4, -1. Am I doing that right? Yeah. And then give me a sec here. And 2 5/3. Asymptote's at 2, given the d value, or the vertical shift. And there you go. Domain's all real. Range is -2. Okay, we're cool. All's good. Yeah. Sweet. Okay, last bit. Natural base of E. You guys should be familiar with E from last year, I think. E is just a number. It's 2.718, whatever. It's Euler's number. If you're curious where how E came about, E roughly equals this scenario here. As x approaches positive infinity. If you make x really big, this fraction is tiny, right? But this exponent gets really big, but there's a trade-off, right? Like, sure, this gets smaller, but this gets bigger. Overall, this number converges towards this. That's how Euler's number. There are some modeling things, some kinds of science that kind of follows this pattern of behavior, so that's where it plays a role, in case you're curious. Yes, a lot of real world applications use this kind of a base. I can't think of any top. Well, I can think of one. Compounding interest continuously does that because we do it in algebra 2. There's some other things I think like half-life, decay, stuff like that follows it. But regardless, just we're going to work with it, right? So a gray wolf population is modeled by the following equation. It has E in it. X is the number of years after 1978. What will be the population in the year 2028? How much time has passed between those 2 years? 50 years, right? So 50 years has passed. So 1.26 times E, 0.247 raised to the 50th power. And yeah, it's pretty easy, actually. It's not that hard. So you can see this is a pretty easy section, guys. This is a kind of a joke of a section, to be honest with you. 1.26 times E is second ln. It's right there. 0.247 times 50. Yep. So, wow, that's crazy. 291 thousandths. And we'll round to nearest whole number. Wolves. So, well, anyway. Not sure that's really a stimulating problem, but okay. That's the notes. We're all done. Actually, I can start grading your test right now if you want to. Here's the homework. Homework's just graphing. Due tomorrow. Okay. And I'll have more clarity of what the students will look like in the casing things. Hopefully there's clearly Friday. I like take